UV visible spectroscopy part 2 is the present video. And now you are familiar with me. I am Saurabh, and let's proceed right into the subject. In my earlier video, we have been talking about some fundamentals of electromagnetic radiations. For example, what is an electromagnetic wave? There is an electrical component and a magnetic component, and so on. That's a particular direction that they are propagating in space. So that kind of thing that we have studied, and we have discussed about some quantum mechanical relations, like E is equal to h nu, where nu is frequency, h is the universal Planck's constant, and it has got some quantum fixed value 6.627 10 power minus 27 ergs into second, and its joule is 10 power minus 34 joules into second. So this is how the energy of electromagnetic radiation is seen in that context. And then we have also studied that there is a complete range of electromagnetic radiations. We have visible radiation, which is a very small part, as you can see, that goes from 380 nanometer to 750 nanometer. And if you talk about UV visible both, then it is around 200 to say around 350 nanometer or 380 nanometer is the UV range. And apart from this, there is a long range of gamma rays, X-rays, and so on, the high energy waves. And low energy waves are the IR or the radio waves. So this we have studied in our earlier session. Now, this video is actually dedicated to the laws of photochemistry, laws of absorption of radiation by certain material, by certain chemical species, and what are the laws that govern the absorption of electromagnetic radiation that we are going to see in this video. A very early law, just like we have some laws of thermodynamics, there is also the law of photochemistry. That is known as the Grothes-Dropper law. And that says that only that light which is absorbed by a system can cause a chemical change. केवल वही लाइट, वही ऊर्जा, वही प्रकाश जो अवशोषित होता है, वही रासायनिक परिवर्तन के लिए जिम्मेदार है. ये बनी बनाई बात है. One photon can be absorbed by one molecule, so there could be 1:1 analogy. But only that light which is absorbed by a system can cause a chemical change. And what is the chemical change? When you are talking about UV visible energy, they are responsible for electronic transitions. In atoms, one electronic energy level to other, and when you talk about molecules, there are molecular orbitals, promotion of electron from bonding to anti-bonding or non-bonding, and so on. So this is the first law of photochemistry that is known as the Grothes-Dropper law. But the interesting law is something else. And before going to this, let us have some idea what would happen if light is incident upon a chemical species or a liquid. It can be a solid or a gas also, but generally when you talk about liquids, when light incident upon a species, it gets reflected, refracted, transmitted, scattered, or absorbed. So if you have a beaker that contains some chemical species, and if you incident some monochromatic light of intensity say I0, then a part of light might be absorbed and a part of light might be rejected or transmitted. Some part of light may be scattered at right angles, and a very small part of the energy can be reflected back. So there are many things that would happen, but mostly and most importantly, monochromatic light would be absorbed and the rest of the light would be released, that is called a transmitted light, and some of the light is going here and there. But roughly speaking, I0 minus IT must be equivalent to the I absorbed. मतलब जो हमने डाली लाइट है और जो बाहर निकल गई लाइट है, जो निर्गमित लाइट है, उन दोनों का अंतर ही अवशोषित लाइट प्रकाश की बराबर होना चाहिए. दिस इज द कोड अंडरस्टैंडिंग. हालांकि दूसरे प्रकार के प्रकाश का भी देयर इज some loss. Now, when we talk about the Stark-Einstein's law of photochemistry, uh, which is also known as a second law of photochemistry, it states that for each photon of light absorbed by a chemical system, only one molecule is activated for subsequent reaction. मैंने अभी थोड़ी देर पहले आपसे कहा था एक लाइट का फोटोन एक मॉलिक्यूल से एब्जॉर्ब हुआ और उसके बाद में वो रासायनिक परिवर्तन के लिए जिम्मेदार होगा बशर्ते कि कोई दूसरी केमिकल चेन रिएक्शन न हो. So, one molecule is activated by one photon. This is known as the Stark-Einstein law of photochemistry, and that is, that it goes somewhere in the quantum yield or quantum efficiency later on. So now we are going to talk about the Lambert-Beer law. That's a very popular law in photochemistry. जितने भी इंस्ट्रूमेंट्स हैं जो स्पेक्ट्रोफोटोमीटर हैं या कलरीमीटर्स हैं या इवन IR स्पेक्ट्रोफोटोमीटर्स हैं जिन पर एब्सॉर्प्शन ऑफ लाइट का मेजरमेंट कैलकुलेट करने का या ज्ञात करने का जिम्मा होता है, दे आर गवर्न्ड बाय द लैम्बर्ट-बियर लॉ, a very fundamental, very important law of photochemistry, which tells that the amount of light is influenced, the absorption and the absorption of light is influenced by the amount of concentration or solid present in the solvent and the thickness of the medium. So there are two different things, but then we'll see one by one how it goes. So this law gives the probability or rate of absorption of light by medium. Actually there are two laws, दो नियम हैं जैसा मैंने आपसे कहा. पहला लैम्बर्ट ने दिया था और दूसरा बियर ने दिया था. And combinedly there is known as the Lambert-Beer law. And what does it mean? उसका मतलब क्या है थोड़ा सा अपन देखते हैं अपनी next slide में. So there's a Lambert law. When a ray of monochromatic light passes through an absorbing medium, its intensity decreases as the length of absorbing medium or thickness of the layer increases. Now this is, we are talking about the thickness of the medium. We are talking about this. Now if the thickness is shown into this, if there is monochromatic light of intensity I0 and if there is transmitted light IT, then what matters is the thickness, as you can see, of the system under investigation. So amount of light absorbed depends upon the thickness of the medium is the concern of the Lambert. Actually, this law is not that simple. There is some mathematical manipulation that we'll see later. However, the Beer is also saying the same, except that the light also depends upon the concentration of the solute in a particular solvent. So this law demonstrates the relation between the concentration of the solution and the absorption of light. So the amount of solute that is present in solution matters a lot now. That is the concentration. So when a ray of monochromatic light passes through an absorbing medium, its intensity decreases as the concentration of absorbing medium increases. This is, we call as the Beer's law that connects the concentration with the amount of light absorbed. In earlier case, we have seen the relation between the amount of light absorbed and the thickness of the medium. Now, these were two independent laws, and then it can be clubbed together to give what we call as the Lambert-Beer's law. The quantity of light absorbed by a solution is directly proportional to the concentration of solute and the path length of the light through this solution. As I told you, now there are two parameters come into existence. दो चीज़ें सामने आती हैं. एक तो सॉल्यूशन की कॉन्सेंट्रेशन क्या है, सॉल्यूट कितना मिला हुआ है, और दूसरी बात यह है कि उस मीडियम में जिसमें से लाइट डाली जा रही है उसकी थिकनेस क्या है. ऑब्वियसली इन दोनों ही बातों पर एब्सॉर्प्शन लाइट का डिपेंड करेगा. एज यू सी इन दिस फिगर, I0 मैंने लाइट डाली, IT बाहर निकली, लेकिन वो निर्भर करेगी इसके कॉन्सेंट्रेशन पर और इसकी थिकनेस के ऊपर, दोनों के ऊपर इस बात होगा. मैथमेटिकली स्पीकिंग, इट इज़ -di/dt इज प्रोपोर्शनल टू I itself. The rate of decrease of intensity of incident radiation with respect to the thickness of the medium is directly proportional to the thickness of the medium itself. and so on. So very interesting, we can go for some mathematical manipulation, and ultimately it comes out to be the first order kinetic type of solution where some logarithmic function comes into picture. That's very interesting thing. So mathematically, if you do some manipulation and all mathematics and you get a generalized equation, it comes out to be log I0 upon IT is proportional to CL, where the A is known as the absorbance or optical density, and as I told you, I0 is the amount of is the intensity of the incident radiation, IT is the transmitted radiation, C is the concentration, L is the length of the medium in centimeter. So when I say log I0 upon IT, it is now actually called as the absorbance. जब हम एब्जॉर्बेंस की बात करते हैं, इसका मतलब हम I0 अपॉन IT के लॉग की बात करते हैं, जिसका आधार 10 है. इट्स लॉग बेस 10 I0 अपॉन IT. दिस इज वी कॉल एज द एब्जॉर्बेंस, और बहुत लोग इसको ऑप्टिकल डेंसिटी कहते हैं. आपका जो इंस्ट्रूमेंट है, जो स्पेक्ट्रोफोटोमीटर है, जो कलरीमीटर है, वो ऑप्टिकल डेंसिटी को सीधे सीधे नाप के दे देता है. सो ए इज प्रोपोर्शनल टू C इंटू एल. C इज कॉन्सेंट्रेशन ऑफ द सॉल्यूशन इन मोल पर लीटर, L इज लेंथ इन सेंटीमीटर, and if I remove proportionality symbol, I get A is equal to epsilon CL. Now epsilon is nothing but called as molar extinction coefficient. That's a very unique feature of a particular solution or a particular sample under investigation, and depends upon number of things that we are not going to talk here. Its unit is liter per mole per centimeter. So it's obviously A is equal to epsilon CL is a very simplified version of the Lambert-Beer law. Is a very simple statement. Now, if I say what is the relation between absorbance and transmittance, when we talk about transmitted light, we talk about the amount of light that is coming out of the sample. कितनी लाइट बाहर निकल गई है, और कितनी लाइट बाहर निकल गई है ये जानना बहुत अच्छा होता है जब हम उसको परसेंट में डालते हैं. मान लो मैंने 100 लाइट डाली है और 50 लाइट बाहर निकली है, इसका मतलब 50% लाइट जो है वो एब्जॉर्ब हुई है. तो मेरे पास यदि दो चीज़ें हैं, तो एब्जॉर्बेंस और ट्रांसमिटेंस, यहाँ दो जो अलग अलग शब्द आए हैं, क्योंकि एक तरफ मैं कहता हूँ log I0 अपॉन IT इज इक्वल टू द एब्जॉर्बेंस, बट when I say further that what is transmittance, so absorption is the amount of light absorbed and transmittance is the amount of light transmitted, it's okay. But how we meaningfully can give in some of mathematical relations, and that would go as transmittance T is defined as IT upon I0. Now it's just reversed, in the absorbance we talk about I0 upon IT and its log. Transmittance, there is no log. I am saying simply IT, the amount of light, and amount of light that is transmitted, amount of light that is is imparted on the material, so intensity of lights, and therefore IT upon I0 is now referred as T. We want to see mathematical relation between this. So as we know that log I0 upon IT is equal to A, and I0 upon IT is T, so that goes as the log T is equal to minus of A. And when we say that log T equal to minus A, and if I want to express T in percent, so I'll do a little mathematics. I will just multiply it by 100 divided by 100, and so there is no net change in the value. And when I say log percent of T into 100 minus log 100 as log M by log N is log M minus log N. तो log 100 माइनस हो गया, and that is equal to minus FA. Log 100 is nothing but log 10 to the power 2. It goes other side. Yeah, so log percent of T is equivalent to minus A and plus 2, because log 10 is also equal to 1. So log percent transmittance is equal to absorbance, negative of absorbance, plus 2 additionally, because we wish to express in percentage terms. And that demonstrates everything now. You can now calculate. If you know the transmittance, you can find the absorbance. If you have absorbance, you can know it. Transmittance, they are the same different phases of the same coin. That's it. So I have given a table between the transmittance and absorbance. You can calculate by yourself by the expression that is given in the red terms. So if there is 100% of transmittance, absorbance would be 0. 95% light is transmitted, so very small the light is absorbed, that's only 0.02. Now similarly go on 90%, that's only 0.046. Now the amount of transmitted light is decreasing. Now the transmitted light is decreasing, it means that absorbed light is increasing. So you must have an increased value of absorbance. And if you see, for 95% is 0.02, for 80% is 0.1, for 50% is 0.3, for 20% it is 0.7, for 10% is 1, and for 0% it is 2. So it is changing exponentially, as we can see in the next in the next plot. So on the one side you have absorbance and you have other side transmittance. At a 0% absorbance, transmittance, you have an optical density of 2, and as you gradually move towards 100% of transmittant, and the optical density or absorbance goes to 0. So this is a relation between the percent transmittance and absorbance or the optical density. Before going for a finishing statement, there are two things that we would like to discuss. Number one, how would we check that Lambert-Beer law is correct? And number two, what are the limitations of Lambert-Beer law? There are two things that we need to discuss before winding up this subject. First thing is, as we have seen, that A is equal to epsilon CL, and if I say that the length of the cuvette or the length of the test tube or the length of the path is fixed for 1 unit, maybe 1 centimeter. So A is proportional to C now. It implies that absorbance or optical density directly depends upon the concentration. You vary the concentration and there is a varying value of optical density. So there is a linear relation between the optical density and the concentration. तो अगर मेरे पास कुछ एक ही सॉल्यूशन के 10 सैंपल मैं अलग अलग कॉन्सेंट्रेशन के तैयार कर लूँ और उनके अगर मैं एब्जॉर्बेंस इंस्ट्रूमेंट के द्वारा नोटिस करूँ, जो एब्जॉर्बेंस अपन कहलाता है स्पेक्ट्रोफोटोमीटर या कलरीमीटर, तो वो उसकी जो ऑप्टिकल डेंसिटी या एब्जॉर्बेंस की रीडिंग देगा, तो वो डेटा और इसकी कॉन्सेंट्रेशन के डेटा का प्लॉट है वो लीनियर होगा. और अगर लीनियर है, इसका मतलब the law works well, and whatever statement given by Lambert-Beer are correspondingly correct. और ऐसा हम देखते हैं कि वास्तव में there is a linear relationship between optical density and the concentration. However, in large number of cases there are deviations, and in many cases we see deviation. It does not always go smoothly. So what are the important deviations? Number one, at high concentration, at say, it generally works at a very low range of concentration. 10 to the power -3 is ideal. But when you talk about 0.01 molar or less, the concentration is high, the amount of solute is high, the electrostatic interaction between molecules are larger, and therefore deviation through the Lambert-Beer law is very prominent. So that's a very prominent part. That is the high concentration. It fails in high concentration, it deviates at high concentration, and it works very good at low concentration, as low as 10 to the power -3 to 10 to the power -5 moles. Scattering of light due to particulates in the sample. If your sample is not clean, there are solid particles, there are particles which have significant colloidal range, they would scatter the radiation, and it is going to cause the deviation. The fluorescence or phosphorescence are the phenomena that might take place by the absorption of light. The molecule go to some excited or singulate state, and then it may not come immediately to the ground state. It can come via releasing energy by different modes. So fluorescence and phosphorescence are the issues that we are going to discuss in next video also. So these are the processes, if they take place, they are going to limit the Lambert-Beer law. ये निश्चित रूप से नुकसान पहुंचाएगा. चेंज इन रिफ्रैक्टिव इंडेक्स एट हाई एनालाइट कॉन्सेंट्रेशन. कभी कभी एनालाइट कॉन्सेंट्रेशन या जिसका हमको एनालिसिस करना है उसका कॉन्सेंट्रेशन ज़्यादा हो तो भी डेविएशन देखने को मिलेगा. शिफ्ट इन केमिकल इक्विलिब्रियम एज ए फंक्शन ऑफ कॉन्सेंट्रेशन. इफ सम काइंड ऑफ शिफ्टिंग इज टेकिंग प्लेस इन इक्विलिब्रियम, सम काइंड ऑफ प्रेसिपिटेशन इज सीन, देन इज गोइंग टू अफेक्ट. नॉन मोनोक्रोमेटिक रेडिएशन. अगर आपने मोनोक्रोमेटिक रेडिएशन का इस्तेमाल नहीं किया है, मिक्स्ड रेडिएशंस का इस्तेमाल किया है, तो ये बताना मुश्किल होगा कि कौन सा लाइट ने किस केमिकल चेंज को प्रभावित किया है, एंड देयरफॉर इट विल लूज इट्स एप्लीकेबिलिटी. And stray light, if your things are not there properly closed, and some light from some other part is coming to this sample, then it's going to affect the entire process of absorption. So there are many things that is going to affect Lambert-Beer law. Lambert-Beer law को प्रभावित करने वाले कई सारे कारक होंगे, मुख्यतः सॉल्यूट का कॉन्सेंट्रेशन ज़्यादा होना, नंबर 2 फ्लोरेसेंस और फॉस्फोरेसेंस जैसी कोई घटनाएं होना, या कोई शिफ्टिंग होना, या फिर के कोई दूसरे प्रकार के रेडिएशन की उपस्थिति, ये सभी लैम्बर्ट-बियर लॉ को प्रभावित करेंगी, जिससे हमको उसका उचित लाभ नहीं मिल पाएगा. सो दैट्स ऑल फॉर नाउ. Thanks for watching this video. I hope you have enjoyed this complete course. Thank you.